Hello, this is Ocean Movements, which is lesson two. So the focus question today, how does the land influence the ocean's movement? We've got different ocean currents that are influenced by the winds, but obviously when you've got continents in the way, then the ocean currents have to move around. And it causes them to form circular patterns, kind of similar to the wind currents. All right, so just a review word, prevailing westerlies. The reason we're talking about this is because this is what causes the wind pattern, but it causes the ocean currents to curve similar to the Coriolis effect. So we'll look at that today. All right, so with oceans, we have waves. And so a wave is just a rhythmic movement. Right now, we're talking about oceans, but a wave could be a sound wave, it could be a radio wave. So it's just a rhythmic motion that causes or moves energy. So in this case, we're talking about waves, and that is wind blown currents. So waves are wind driven. The highest point of the wave is called a crest, and the lowest point of a wave is called the trough. So here's kind of the diagram of what that looks like. So we've got the crest, which is the highest point of the wave. So you can see right here, right here. If we measure from crest to crest, that would be the wave length. And then the trough is the lowest point. So just like a trough, like, a pig or something would eat out of. So it's this low, like, bowl. So that's the trough. And then the crest is the peak. The height of the wave is measured from trough to crest. So from low point to high point. And then the wavelength is measured from crest to crest. So in storms, we're going to get a bigger wavelength and a higher height of the wave. All right, so the wave height depends on these three things. It depends on fetch, which is the distance that the wind blows. So, for example, if the wind is blowing super hard on Mary Lake, we're not going to get very big waves. We might get little white caps, but we're not going to get like ocean waves, no matter how hard the wind blows, because the fetch is small. But on the ocean, the fetch is, thousands of miles. And so that's going to be a very long duration. That's going to cause more bigger waves. And then wind duration, how long does it last? So is the wind blowing for hours or is it blowing just for minutes? And then you've got wind speed. So is it blowing really fast? Is it blowing really slow? So waves depend on those three things. So this is why in the ocean, you're always going to have bigger waves. Or a bigger body of water, you're going to have bigger waves because you've got a bigger fetch and potentially more duration of wind, and then, of course, wind speed. All right. So looking at the waves, here's our wavelength from crest to crest. Wave height is from trough to crest. And so notice how the waves are coming in. And so if you've ever really sat at the ocean or kind of watched the ocean waves, out in the ocean, they look like they don't really look like waves at all. But as they come in, notice what happens. So here's the wave height. And so as it comes in, it's starting to drag along the shore. And so what happens when it drags along the shore is it causes the wave height to change. And so the bottom of the wave, basically, when it says down here, when depth is less than half the wavelength. So let's say the wavelength is 10 feet. So when the shore is 5 feet deep, then the bottom of the wave starts to drag on the bottom. So the wave energy is also below the wave. So it starts to drag on the bottom and the wave grows in height because the energy is all there. So the energy has to go somewhere. So it grows in height as the bottom of the wave starts to drag, and that causes the wave to grow. So that's why when you're at the shore, you'll see waves come in and then all of a sudden they look like they get higher and then they topple over. And so that would be this breaker. And so when they break, and that's what people would want to surf on or bodyboard on or whatever, then that is called a breaker. And so it's just breaking basically. And then it comes in. So this is generally what people see when they're sitting at the ocean. You generally don't see these. You can. I mean, they look like big, long ripples coming in. But that is kind of the idea of the wave. So that's when they break, they're called breakers, when they crest and fall over. All right, and then something else that we're going to talk about a little bit now, and then we also talk about in astronomy is tides. So tides are the periodic rise and fall of the ocean. And so for tides, we have high tide and we have low tide. So high tide means the water is at its highest point. Low tide means that the water is at its lowest point. And so it goes a couple times a day from high tide to low tide, and it follows the moon. So the tides basically follow the moon and then a little bit of the sun, and it's basically because of gravity. So we've got here high tide, and this is a 24-hour period. So in this case, it's called a semi-diurnal tidal cycle, and we've got we've got two high tides a day and two low tides a day. So that's semi-diurnal. Then we've got a mixed tide, and this is what we have in California. And it just happens to be where you're located on Earth, where the wind patterns are, where the continents are compared to the ocean basin. So it just happens to be in California that we have a mixed tidal cycle. So we have two high tides and two low tides a day, but notice how one high tide is much higher than the other. This one is even, so everything is even. This would be pretty typical along the equator. And so the mixed tide, we've got one really high tide and one kind of high, semi-high tide. And then same thing with the lows. So if you look at the tidal cycles, if you go to Eureka and you want to go to maybe Agate Beach and find agates, then you'd want to go on the lowest of these, and that way you can see more shore and more agates. And then same thing with tidal pools. If you wanted to go look at tidal pools, you'd want to go during the lowest tide so that you can see the most tidal pools, which are where the little sea stars and stuff like that are when the tide goes out. Let's see. And then the last one is diurnal. So diurnal, there is 24-hour period, and basically there's one high and one low a day. So just one tide. And this is in a variety of places across the earth. The most common, though, are these two. So diurnal is not as common, but these are the most common types. And like I said, in California, we have the mixed tide.
This shows 12 hours at the famous Bay of Fundy in Nova Scotia, Canada. It's the biggest tide change in the world. But what force could move such a massive body of water? Gravity. Here's the Earth rotating on its axis every 24 hours. We'll now draw the Earth as a diagram with its surrounding layer of ocean. And to the right is the silvery moon. Everything is attracted to everything else in the universe with the force of gravity. So the moon is attracted to the Earth, and the Earth is equally attracted to the moon. Notice that the two force arrows are the same length, showing that gravitational attractions are of equal strength. But we're only interested in the force on the Earth here. The moon pulls on the ocean closest to it and makes it bulge outwards. When the Earth rotates, the sea level is higher at this point in its rotation, causing a high tide. And a low tide where the oceans don't bulge. So you'd expect one high tide each day. But here it gets interesting because there are two high tides a day. How come? This is because the strength of gravity is greater when objects are closer. We'll call the location of the ocean on the near side of the moon, point A, at the center of the Earth, point B, and at the far side ocean, point C. The strength of the moon's gravity is strongest at A because it's closest to the moon. So the part of the ocean that bulges towards the moon most is at A. But the moon's gravity also pulls on the Earth, moving it towards the moon as well. This has two effects. First, it makes another bulge at C. Second, it fills in the bulge at A, but not completely, because A has moved further towards the moon than B. Lastly, the far side ocean at C is also attracted to the moon, but it moves least because the moon's gravitational pull here is at its weakest, being farthest from the moon. This leaves a partial bulge at C, though not as big as the one at A. Now we can see why, when the Earth rotates through 24 hours, it goes through 2 high tides and 2 low tides. But there's another surprise. By the time the Earth has rotated once and arrived back at its original position, the moon has moved on a bit because it's orbiting the Earth at the same time. That means that the Earth has to catch up with the moon, so the next day's high tide is about 50 minutes later. The moon rises and sets about 50 minutes later too, because the Earth has to catch up with its orbiting moon. You can even test this by timing the moon rise or moon set from one day to the next. Or check out some tide charts to see if the tides obey this rule too.
All right, so it's pretty cool how it goes in so much. So the Bay of Fundy with the different tidal ranges, it's pretty crazy. Let's see, we don't watch it again. All right. So if we look at the moon's influence, like what the video talked about, so the moon has a big pull on the Earth, and so we don't really realize that, but we realize it when we look at things like the ocean that aren't physically like they're able to slosh around and move around. And so wherever the moon is, and the moon, as the Earth spins in 24 hours, the moon is staying there. The moon does orbit the Earth, but it takes 29 days to do that. And so that's why we have a full moon every 29 days. So, so as the moon is here and the Earth is spinning, the tides basically are drawn towards the gravity of the moon. And so on the other side, it's kind of like centrifugal force. So if you're sloshing something around, you're pushed out to one side like a bucket of water. That bucket of water is pushed out to one side, but if it was round, it would be pushed out to the other side too. Or if you have like a water balloon and you spin a water balloon, it'll flatten out on all sides. So that's kind of similar to what's happening here. And so this is where we have our low tide. This is where we have our high tide. And then same thing, low tide here. This would be all the way around the Earth. So low tide here, high tide. So that's why in general we get 2 high tides and 2 low tides a day. Along the equator, it's pretty steady, 2 highs, 2 lows. As you get farther up, you get one higher tide, one lower tide, because the moon is not always here. Sometimes the moon is here, sometimes the moon is here. And then up here, you get more of the diurnal, which would be one high tide, one low tide a day. All right, and then the sun does influence too. So you like you saw in the video, the sun also pulls as well. So sometimes the moon and the sun are perfectly lined up, and you get a really high tide. And then sometimes they're at a 90-degree angle, so you'll get the moon here and you'll get the sun here, and so they're kind of being pulled both directions. So you get kind of a average high tide, but they do both pull on the Earth. The moon has more of an influence. It's much smaller, but it has more of an influence because the moon is closer. And so it influences it a little bit more. All right. So I mentioned that sometimes we get really high tides, sometimes we get just normal high tides. And so the 2 types of tides are called spring and neap tides. So a spring tide does not mean it happens in the spring. A spring tide actually happens twice a month. And a neap tide happens twice a month. And so a spring tide is when you get higher than normal tides. And that's when you have the sun, moon, and earth are all aligned in space. And so you get the sun and the moon both pulling the same direction. So it causes those tides to be higher than normal. Then it also means that the tides are lower than normal during low tide. So if you're going to Agate Beach or you're going to look at tidal pools or something like that, you would want to go during spring tide because it's your lowest tide. So it'd be the best. And then neap tide is when you have first and third quarter moons. So if you look up in the sky, it would look like half a moon. So that's when the moon is here and the sun is here. And so it's kind of this 90-degree angle. So you've got the moon pulling one direction, you've got the sun pulling another direction. So it causes them to be kind of an average high and average low. So those are spring and neap tides. All right, and so here's that diagram. So you've got this spring tide where you've got a full moon and a new moon. This is what it looks like compared to the sun. And so notice how they're all in a straight line. So the moon is pulling this way, the sun is pulling this way. So you've got it in one direction. So you're getting a higher than normal tide. And then neap tide just means that it's first and third quarter of the moon. So the moon would look like a half in the sky. So you've got this 90-degree angle. So you've got the moon pulling this direction. You've got the sun pulling this direction. So you've got kind of an average high and average low tide. All right. And then if we look at currents in the ocean, so there's lots of ocean currents, and currents, there's a lot of a variety of currents. So there's not just one type. On the surface, we have wind currents, and that's the resultant of wind. And those are mostly our wind patterns, like the trade winds, the westerlies. We have the polar easterlies, all of those. And so then that's called surface currents. So those are wind-driven currents. And then we also have other currents. We have density currents and temperature currents. So those are both densities. Density is temperature and salinity, so saltiness. So you've got the surface currents, which are wind-driven. And so the wind-driven currents, like we learned with the Coriolis effect, wind is in a circular pattern. So the wind currents go because of the Coriolis effect, they are deflected and turn into kind of circular patterns. And then the oceans follow that same pattern, right? Because if they're wind driven, then they're going to follow that same pattern, and they're called gyres. So gyres is a circular pattern. So we'll take a look at that. So here are the gyres. And so you can see here is in the northern hemisphere, they're going clockwise. And same thing with this, because that's what the wind currents are doing. So as the Earth spins counterclockwise, the Earth is spinning this direction. It's causing those winds to move in that direction, so they are deflected. So here's our trade winds, and then here's our westerlies, and then up here we've got our polar easterlies up here and down here. So in the southern hemisphere, it's the opposite. It's counterclockwise because that's what the wind patterns are doing. And so they're just mimicking the wind patterns. So here we've got the trade winds, and then it meets up with the westerlies, and the westerlies blow across. And we've got a big gyre here. So the oceans are driving that. Notice the blue versus the red. So here, remember how I mentioned that California has cold water? So the California current comes down from the north, so it's cold. And then notice how all of the the west coast of every continent are cold currents. And then on the east coast of every continent, it's a warm current. And so the east coast of every continent is warmer in temperature than the west coast. And that's because of the ocean currents, and that's how they influence weather. All right, so then we have, if we go back to this, we've got this current coming down. And so what's happening is the water has to be replaced. If it's blowing down, it needs to be replaced by something. And so it's replaced by something called upwelling. And so here's the current. So this is looking at California. And so what happens is the current is moving along like this, and it's drawing that water out. So the water doesn't just disappear, it's replaced by the water from deep underneath. And so this is called upwelling. And upwelling creates nutrient rich water. So that's why we have so much life off of our coast, like whales and sea lions and seals and all kinds of things off of our coast, because this is nutrient rich water. And that nutrient rich water is feeding all of the organisms that feed everything that's higher up on the food chain, like the whales and the sea lions and all of that. So we've got lots of life off of California's coast because of All right, and then we have something called density current. So that's all that stuff that we talked about was all surface. So this is density currents, and so density currents are driven by temperature and salinity, and they're happening deep underwater. So you can see here, look at how all the oceans are connected. So they're all completely connected here. And so we've got this cold water. So the coldest, densest water, like we talked about on Tuesday, the coldest densest air or water sinks and it flows along the bottom and it flows all the way until it gets near the equator, which is right in here. And so then it warms and is replaced by warm water. And that warm water, so that's where upwelling occurs. And then that warm water is warmed at the equator because that's where we have the most radiation. And that warm water travels all the way back up because of density differences, just like you guys saw in on Tuesday at the in the lab that we did in class. So we've got these density currents that are driven by temperature, and then they're also driven by salt. So they're driven by two different things. But and this could take thousands of years, but water can travel throughout all of the ocean basins. It's all connected.
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean's surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres. And because water holds onto heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue to study currents and the powerful forces that shape them. What about the creatures that adapted to survive?
So it's kind of amazing how tied together everything is. Oops, it's always going to start again. So pretty amazing how it's all tied together. Let me get this going here. All right. Whoops, starts over. All right, so pretty amazing how it's just all tied together. That last video. So looking at the gyres and the Coriolis effect and how all of the air, like it tied in with the air masses that we've talked about, and the global wind patterns and the ocean currents and how it just moves and circulates the air around. It's pretty amazing and pretty intricate how connected it is. So hopefully you enjoyed that, and I will see you next time.